Hello everyone, and welcome back to this series on MATLAB programming. Today we're going to be taking a look again at solving ordinary first-order differential equations, but instead of looking at, for example, exact solutions or slope fields, we're going to be looking at a few numerical methods that definitely anybody should know when solving ordinary differential equations. Now there are packages and toolboxes already out there, but what we're going to do is we're going to manually write our own numerical methods. And that, of course, gives you a lot of flexibility in terms of modifying them, improving them, or maybe even creating your own that don't already have packages out there that probably might be better than the ones that have already been developed. So, the differential equation or initial value problem that we're going to be looking at is this very simple linear equation. Y prime is equal to sine x minus y, with y of minus 2 is equal to 3 as the initial condition. So the very first thing that we need to do when analyzing a differential equation is to define our function f. So f is going to be the right-hand side of our ODE when y prime has been oscillated. So obviously we have a function of both x and y, and even if it's not a function of both x and y, sometimes it's safe to put ampersand x comma y there just to be safe. So we have sine of x minus y as our function, and let's just define our initial condition values x is 0 and y 0. So x 0 is defined to be equal to minus 2, and y 0 is going to be equal to 3. Now, if you know how to solve analytical differential equations, in particular first order linear and homogeneous ODEs, I definitely invite you to maybe pause this video and see if you can find the exact solution to this initial value problem. And if not, you can just trust me about the next statement. So the exact solution, which I'm going to abbreviate by f subscript ex for exact, is going to be, again, a function of x only, i.e. you can get an explicit representation for this analytical solution, and then the general form is going to be equal to c times e to the power of minus x plus sine of x divided by 2 minus cosine of x divided by 2. So that's the general solution, and for this constant c, for the particular solution that satisfies this particular initial condition, one can find that this is going to be equal to, generally speaking, e to the power of x0 times y0 plus 1/2 times the quantity cosine of x0 minus sine of x0. Right, so regardless of these x0 and y0 values, this is the general formula for that arbitrary constant c in that general equation for a particular initial condition, right? So that is going to be our exact solution that we're going to be comparing our numerical methods to. Right. So the next thing that we need to figure out is how far from the initial condition x value of minus 2 do we want to forecast into the future. I'm going to choose a final value, which I'm going to call xf, to be equal to 1. The only requirement is that this, of course, must be bigger than x0. That's the only requirement. Of course, the higher the value of xf, the longer this method is generally going to take. And the next thing we need to do is define the domain steps that we plan to take, which I'm going to represent by dx, which is just the coding form of delta x, actually. It's not an infinitesimal. Let's just choose a value of 0.01. That's a decent value. It's not going to take too long, and it's going to give us pretty decent accuracy. And the domain value, which I'm going to represent by capital X, this is going to be equal to x0, so it's going to be a vector. So x0 to xf spaced out by dx, right? So that's going to be our domain for our functions and our numerical solutions as well. So what I want to do is I want to plot our exact solution so we know what we're comparing to. So what I want to do is I want to plot x and then the exact solution ex of x, and then I'm just going to plot this in black. For the numerical solutions, I'll do in other colors like red, green, and blue or something like that. So k is the letter for black, and then that's going to give us our solution. Let's give a nice little title for our final graph, which is going to be numerical solutions for the differential equation dy over dx is equal to sine of x minus y. Right, so that's the differential equation we're solving, and the syntax that we're writing this interpreter, and writing this thing in is, of course, LaTeX. Right, so that's going to give us our nice solution. And that's pretty much it. So if we give this function a run, that is going to be our exact solution. So hopefully whatever numerical solutions that we do get out of this, hopefully they are close to this black curve. Right? So the next thing that we need to do is we need to start setting up our numerical methods, right? So what I want to do is first off define the number of points that are going to be inside of my numerical solutions. Okay, so how many points are we going to be calculating? So n is going to be equal to xf minus xo divided by dx, and then plus 1 since we have that initial condition at the very end. Of course, make sure that this is an integer. Sometimes if you choose a weird dx value and you have some weird xf and xo values, sometimes you have to sort of floor this or round it down or round it up. Just make sure that n is a integer, a positive integer moreover. So once I have that, then I need to initialize my vectors where I'm going to save all values of my numerical solution. So what I'm going to do is I'm going to do three methods. I'm going to do the Euler RK1, the Midpoint RK2, and the Classical RK4 methods, and then show, is one better than the other and by how much. So the Euler method solutions I'm going to store in a vector called YEM, Euler method, and let's just initialize it in terms of memory, in terms of n rows, one column, right? So this is going to store our Euler values, and we already know what the first value of this vector is. That's going to be equal to y0, so let's just initialize that there. And then what we're going to have is YMM, which is again going to be zeros, n rows, one column, and this is going to store our midpoint approximations. And again, we know the first value of this vector as well. This is also going to be y0, and then we're going to have y subscript rk4. Again, same size. That is, we're going to be approximating them on the same exact domain. It gives us a fair comparison. And this is going to be the classical Runge-Kutta Order Four method. Right? And as usual, we know the first value for this vector. Again, it's going to be y0. So once we have all of our solutions initialized, now we're going to go ahead and start coding our numerical schemes. So since we're going to be saving all of our values inside of these three vectors for our numerical solutions, you could probably do a while loop, but I think a for loop is a little bit more clear in terms of the structure for this particular type of implementation. The dummy variable that I'm going to be using here is double I. Don't use single I because that's like the square root of -1, so double I is a good index to choose. And let's start from 2 and go all the way up to n, which is the last value of each of these vectors. And we're starting on the second because we already know the value of the first. Okay, so let's just quickly outline what we have here. So when I is equal to 2, what does this correspond to in terms of our, for example, Euler's method? So our Euler's method is yk plus 1 is equal to yk plus dx times f of xk yk for k is equal to 1. So I equals 2 is the same as k is equal to 1 in that particular algorithm. Okay, so just keep that in the back of your mind when we're doing some of these calculations. So let's first off define what is xk in all of our numerical schemes, because we need that for the evaluations. So xk is going to be equal to the initial step plus some steps into the future of x0, regardless of the value of k. So if we do, for example, plus double I minus 2 times dx, is this going to give us what we want? So when I is equal to 2, what do we have here inside of this expression? notice that when double I is equal to 2, 2 minus 2 is equal to 0, and that's 0 times dx, which is equal to 0, so xk will start at x0. So does that make sense? So y1 is equal to y0 plus dx times fx0, y0. So x0 is the value that we're going to be using to calculate y1. Right? And we can move up to, for example, double I is equal to 3. That's going to be 3 minus 2, which is equal to 1. And that's going to be 1 dx in the future of x0, which is going to be x1. And x1 is used to calculate y2. So this is the correct implementation for that particular time step update equation. Right? So once you have convinced yourself that that is where you want to go, now we're ready to code our, let's start off with the Euler method, which of course is sometimes referred to as the RK1 method. Okay, so EM for Euler method, double I, 1, it's always going to be 1 for that second input because it's not a matrix, it's just a vector, and I don't want it to automatically create a vector when I don't need one. So this is going to be equal to the old Euler method value. So y1 is equal to y0, which is the first element of YEM. So the second element of YEM corresponds to y1. The first element of YEM corresponds to y0. So in some sense, there's a shift of our notation and our implementation because MATLAB starts all our indices at 1 compared to like C++, which starts at 0. So C++, this would make a little bit more parallel sense in terms of the coding. So what we have here, this is going to be equal to YEM II minus 1 because this is starting at 2. We're going to reference the first element, and then this is going to be plus, and then dx, so dx times f of xk, which is already calculated above, and then the old y value, which is YEM II minus 1. Okay, and keep in mind we should be comma 1ing that particular implementation, and let's semicolon that to suppress that output. So that is going to be our Euler method. Let's go ahead and calculate our midpoint method and also our classical RK4 method just to get them out of the way, and then we'll plot all three of them at the very end, and then we'll summarize which is better and by how much. So the next method that we want is the midpoint, which is a particular type of RK2 method. So this is going to have a, an L1 or L2. Some people call it K1 and K2. So L1, and I'm going to use L1A because we're going to have an L1, 2, 3, 4 for RK4 as well, and I don't want those L's to conflict with each other. So I'm going to call this L1A. You can call it L1 midpoint if you want to do that as well. So this is going to be equal to f of xk. In the old y value for the midpoint method though. So YMM II minus 1, 1. Right, so that's the first L1, and then we're going to have L2, which is going to be equal to f of xk plus dx over 2, and then YMM, which is the old I minus 1, 1, plus dx divided by 2 times L1a. So those are our steps in our midpoint method, and then the update equation for it is going to be YMM II1. So II1 will be equal to the old MM, II minus 1, 1, plus dx times L2a. So that is our new y value via the midpoint method. Now let's go through our classical RK4 method. So our classical Runge-Kutta Order Four. So I'm going to call these L1b, L2b, L3b, and L4b. So L1b is going to be equal to practically the same exact thing as these. So in some sense what we can do is we can just copy and paste these down and just make the necessary modifications. So this is going to be B, this is going to be B, and we're going to be referencing the RK4 y value in each of these. So RK4, and make sure you change that to L1b. All right, so that's the first equation for classical RK4. L3b is going to be the same as L2b, i.e. in some sense it's nested in itself, but it's referencing a different point in that sequence. Okay, so that's going to give us our L3b, and then our L4b is going to be equal to, let's see, f of xk. Now keep in mind the L4 does not have any over 2's, so it's just going to be xk plus dx, and then comma y, r k4, I minus 1, 1, and then plus dx times L3b. And that's going to give us our steps for our classical RK4 method. And then finally, y, RK4, our update equation, is going to be equal to II1 is equal to y, RK4, II minus 1, 1, and then plus our weighted average of our L1, 2, 3, 4. So for the classical one, it's going to be dx divided by 6 times L1b plus 2 times L2b plus 2 times L3b plus L4b. And that is going to be your update equation for your classical RK4 method. Right? So those are going to be our implementations for the Euler, Midpoint, and classical RK4. Now let us go ahead and create a plot with all these solutions, including our exact solution, and let's calculate a metric to sort of quantitatively compare the approximations for the correct solution for each of these methods. So up to this point, we've calculated our exact solution to our differential equation, we've plotted it, and we've actually gone ahead and done our numerical solutions for Euler, Midpoint, and Classical. So if we give this a run with just what we just have a graph of our exact solution, but we haven't put our graphs for our numerical solutions inside of this plot. So let's go ahead and do so. So since we already have a figure, we just need to hold on and plot our numerical solutions onto this particular graph. So let's start by holding on whatever we decide to plot at this stage. So we're going to plot, for example, our Euler method on the x-axis. Now keep in mind, x is actually going to be the same for all of them since we're using the same domain, but you can change that up if you desire. On the y-axis, we're going to have the Euler method, all rows, first column of course, and let's go ahead and do this in, let's say, blue lines. The next one I want to plot is going to be x and then the midpoint method. And let's plot this in, let's say, green. Actually, let's do, yeah, green's okay. Green lines. And then lastly, our RK4, all rows, first column. And let's do this in red so it stands out. So blue is going to stand out, and in particular it's going to be the worst. And red hopefully is going to stand out, hopefully going to be the best. And green's probably going to be wedged in between blue and red. That's what we anticipate anyway when we're doing these types of equations and methods, but don't always expect that. There are some extreme cases where it possibly will not fit. The next thing I want to calculate is a error bound or an error metric, and probably the easiest one to do is an average absolute differences metric. So let's do some AAD metrics for the error calculation. So what I want to do is I want to calculate the error for EM, error for MM, and error for RK4. So error for EM is going to be equal to, let's do it as the sum of the, we can do the sum of the sum. Generally it's a matrix, but technically it's a vector. But you can always do sum just to be safe. And let's do the absolute value of the exact solution evaluated on our domain. And then minus the Euler method values. Right? And since it in some sense depends on our number of points that we have, let's divide by n just to make that metric a little bit more smaller. Now, before we proceed, we need to make sure that these vectors fex and ym are the same exact size. So let's just make sure and check what that is. So in this particular implementation, we have fex of x, and let's look at the size of ym of that particular thing, because when we're subtracting them, we want them to, of course, be the same exact size. And notice that they are transposes. So, for example, if we transpose this FEXX, then we get the same exact size. Now, you could, of course, make them the same exact size originally, but sometimes when people implement them, sometimes it changes sometimes, right? And that's perfectly okay, right? So I'm just going to throw a little transposition on top of this FEXX just to make sure that it's comparing the right things, okay? Because keep in mind there's a bunch of ones or zeros in some of those things, and we don't want to be comparing to those zeros that are sort of floating out there in the middle of nowhere. So next we're going to have MM error, so the midpoint method error. This is going to be, again, the sum of the absolute value of our exact solution transpose minus YMM, and then that, still same amount of points. And then we're going to have the RK4 error, again, sum, absolute value, exact solution transpose minus Y, RK4. All rows first, and then divide by n to normalize. So those are going to be our metrics. So now what I want to do, let's create a nice little table to summarize all of our results. So our methods that we considered today are going to be the Euler method, aka RK1, the midpoint method, aka RK2, and the classical RK4 method. So these are the methods that we're looking at here. And then the errors for each of them are stored in EM error, then MM error, then RK4 error. Now when making tables, keep in mind these have to have the same number of rows, same number of columns, and then once we have that, then we can just do a table with method as the titles and errors underneath that. No semicolon after that because we actually want to see that. So let's just give this a run and see what we have. So if we just look at the quantitative methods over here, what we have here is we have an Euler method, has an AAD of 0.006. Midpoint is 1.89 times 10 to the minus 5, which is 0.4018. This has 2 zeros, and our classical RK4 has 9 zeros before that one. So we clearly see that the classical RK4 method is a lot better than the midpoint method, and the midpoint method is of course a lot better than the Euler method. So quantitatively, we obviously see that the RK4 method is a lot better, especially for this particular equation. Now let us look at the qualitative results. So here we have that at least qualitatively, all 4 solutions are approximating the solution pretty well. None of the 3 sort of go off the rails in terms of approximation, which is actually a very good sign. So if we sort of look over here and zoom in, we do see that the blue curve is farther than the other 3 curves. Because keep in mind our exact solution is plotted in black, which is located here, which as you can see, the green and the red are sort of hiding in this realm. So blue is definitely off, but generally speaking, if we look at our exact values, it's not too off, but it's still greater than 0, but it's not as greater than 0 compared to the other 2. So let's just zoom in to sort of see what's going on in this green, red, black area. So as you can see, we have our green here and our red here, and then you're like, oh, where's my black solution? So if we keep on zooming in, we eventually come across it, which is sort of hiding in here. They're very, very, very close, which is a good thing. Red is our RK4 method, keep that in mind. Now, if we sort of zoom out and look at our solutions, you probably see here, at least when I don't zoom out, there is the biggest difference, probably somewhere here where the derivative tends to be changing a lot, i.e. the convexity is really large. So let's actually zoom in there because that's where we can actually see the most detrimental difference, especially with the RK1. So there is our Euler method down there in blue, and then we can zoom in and we can start to see that green is actually very far from red, and if we continue to zoom into the red, where is our exact solution? now it start to appear, right? There it is. Isn't that beautiful how accurate the RK4 method is? Now, of course, there are some methods that are better than RK4, but RK4 definitely gets you a lot of accuracy, even for the easiest implementation that we have done here. So that's how you can do some basic numerical methods and actually in some sense very important numerical methods for solving first order ordinary differential equations. Hope you enjoyed this video and I'll see you in the next one. Take care.